The title of my talk today is Limits of Symmetric Computation. And I want to give, in the context of one brief lecture, give you a flavor of the kinds of questions we've been looking at in a sort of research program on symmetric computation, which tries to make a contribution to understanding the complexity of computation. It comes from the point of view of logic. It was mentioned in the introduction, a lot of my work has done in logic, but I'll say almost nothing about the logic in the course of this talk. I want to say a little bit about what we understand about computation and the complexity of computation coming from this point of view. So first of all, to give you some context, I realize that in this audience there's, some specialists in the complexity of computation and some people who are not computer scientists at all. But I assume many of you have heard at least of the P versus NP problem. So it's, I think, without fear of contradiction, I can say the most famous open problem in theoretical computer science. It's one of the 6 remaining Clay Millennium Prize problems in mathematics, right? So there's a $1 million prize on offer for settling the question either way. And the point is that now it's maybe 45 years or so since the problem was first formulated. And it's not just one problem, because in the space of that, it has spawned a vast discipline of work in the field of complexity theory. So what is the problem about? Something's gone wrong with my slides. But never mind. P is a class of problems solvable efficiently, which means that the number of steps required by an algorithm to solve the problem grows polynomially in the size of the instance. Okay? This will serve as our definition for the moment. NP is usually described as a class of problems where a solution can be checked efficiently, which means there is an algorithm which, given an instance and a candidate solution, can check it using a number of steps that grows polynomially in the instance size. Okay. I don't want to dwell on those definitions, but informally, they're usually described as problems which can be solved efficiently versus where solutions can be checked efficiently. And I'm going to take as an example to start with. Consider the problem of solving a system of linear equations. Okay? So here we have n, little n, is the number of unknowns, x1 to xn, and m is a number of equations. So we have m equations, each of which is some linear combination of the n unknowns on the left and some constant on the right. Okay? And we want to know, does this thing have a solution? Okay? So in other words, the instance, I want to, as we understand, it is a matrix A and a vector B. And we're asking, is there an x such that ax is equal to b, a vector x? That's the question we're asking. So to be clear, what do we mean by the instance size? It's the instance of the instance is the matrix and a vector, so it's really m times n. M times n plus 1 entries is the instance size. But of course, now the question is, what are these individual entries, their numbers, and how do you represent these numbers? If the numbers are rational numbers, right, then we'll talk about the complexity in terms of the number of entries times the number of bits required to write each entry. And if I ask, okay, let's say the entries are rational numbers, rational matrix A and a vector B, is there a rational x with this? We can solve this problem in polynomial time. So there is an algorithm to do it, which works in polynomial time, and this is this familiar Gaussian elimination algorithm, right? Just solve the system of linear equations. To argue that this is in polynomial time, you have to show that actually the number of bits in the rational numbers in the solution can be bounded by a polynomial in the number of bits that appear in the entries that appear, but this can be proved. Okay, I'm just saying there's a technicality there. But for me, the more important thing is that the same argument will work. If you replace the rationals with some finite field k, right? And then everything about bit complexity disappears because now the size of the field is a constant, and the same argument works.
Isn't there a problem that the size of the intermediate solutions, if you have a Gaussian elimination and you divide by them, can have the exponent?
Yes, but it does all work in polynomial time, I think. So yeah, I mean, I wanted to avoid that technicality, which is one of the reasons I just, take as a sort of working example the finite field. Okay. What about if I say, well, my entries are integers and I want an integer solution? Okay. Now I can't use Gaussian elimination because I no longer have division, right? I can't just divide. So Gaussian elimination by itself does not work. We need something a bit more complicated, but there are polynomial time algorithms. I'm not going to go through the details of the algorithm that solve the problem in this case. And just like here, we could pass from the rationals to any finite field, by the same kinds of algorithms that work over the integers, we can pass to any finite ring, and we get polynomial time algorithms for solving the systems of equations over a finite ring. Okay. What about the natural numbers? If I now say, let's say my entries are still integers, but I'm looking for a non-negative integer solution to the system of equations. What can I say? The systems that, the things that worked on the ring of the integers, those algorithms also fail here. The problem is, in fact, in NP. Why is this? This is not completely obvious, right? NP, remember, means if I give you the solution, you can check that it is a solution in polynomial time. Well, it seems easy. If I give you the vector x, you plug it in and you check that it all works. But it has to be polynomial time in the size of the instance. So you have to be sure that the actual solution isn't too big, right? So that the checking process doesn't take too long. And so this requires a proof that, again, the bit complexity, the number of bits required to write the solution, is bounded by a polynomial in the size of the instance, which means that the numbers that appear are bounded by some exponential in the number. The numbers that appear in the solution are bounded by an exponential function of the numbers that appear in the instance, and this can be proved. So the problem turns out to be in NP. That's what it means to be in NP. We can verify the solution, but we know of no polynomial time algorithm in this case, okay? If we're looking for non-negative solutions. In fact, the problem is NP complete. What does NP complete means? Means that if there was a polynomial time solution, then we would have solved the P versus NP problem by, in the most unexpected way, we would have shown that P equals NP. Okay, that everything that is in NP is in P. In fact, never mind the bound, exponential bound, if we just ask, is there a solution consisting of just zeros and ones, that problem is already NP complete. Okay, that's the, so the problem gets hard. So restricting the range of the variables seems to have made the problem harder, right? Going from the rationals to the integers to the natural numbers. One way of understanding this is the following. What does it mean for a problem to be in NP? It usually means that there is some search space of solutions to the problem through which you want to look, and the space of solutions is the size is exponential in the size of the instance. Okay, so for example, if we have n unknown variables and they all take values 0 and 1, there are 2 to the n possible values, 2 to the n possible vectors. This is an exponential size search space to look. Sometimes the algebraic structure of the problem means we can search through the space quickly and converge on a solution. This is what I mean, but what do I mean by the algebraic structure? When this, we were looking at linear equations over fields or rings, there's an algebraic structure to this space. You know, in the case of fields, this space of solutions has the structure of a vector space, and we know that solutions are sort of linear subspaces. That is what allows us to converge to a solution, right? So, for example, if I take my system of equations to be where addition and multiplication are taken modulo 2, this means that, yes, I'm looking at 0, 1 solutions, but I can think of this as a vector space over the two-element field, and then solutions are linear subspaces, so that's what enables me to converge to a solution. But if we lack the algebraic structure, then the solutions to the problem can code any problem in NP in the search space, and that's when we get NP completeness. Basically, the lack of structure means the solution spaces can be very different, and you can code any problem. So for instance, if you look at this as system equations over the integers, then any subset of these 2 to the n possible vectors can be the solution space, right? They're no longer just linear subspaces. And that means that the problem is rich enough to code any NP problem, and you get NP completeness. Okay, so NP completeness is kind of the lack of structure on the space of solutions. That's what NP completeness is about. Now, my example problems so far have been systems of equations. The other kind of problem I want to talk a little bit about, because these are commonly used algorithmic problems, are problems on graphs, right? So a graph is just a set of vertices and a collection of edges, which we can think of as a symmetric irreflexive relation on the set of vertices. Here's an example of a problem in P. The graph is Eulerian if there is a walk starting at some vertex, so you can walk along the edges of the graph and return to the vertex having passed through every edge exactly once. And we know, thanks to Euler, that this is true if and only if every vertex in the graph has an even number of neighbors, and that's a property easily checked, and therefore it's in polynomial time to decide this property of graphs. Less obvious, given a graph, the perfect matching problem is there a subset of the edges so that every vertex is incident on exactly one edge in the subset? This is known as the perfect matching. Does the graph contain a perfect matching? This turns out to be polynomial time, but the algorithm is certainly not obvious. Okay, and it requires some work, but again, you can understand the algorithm as discovering a certain algebraic structure in the space of perfect matchings. I mean, they form a sort of matroid structure, and that's where the algorithm comes from. Some NP-complete graph problems I'll mention. Hamiltonicity. This is, maybe you can think of as a simple version of the traveling salesman problem. You're given a graph, is there a cycle starting at a vertex V, which returns to that vertex and passes through every vertex exactly once, right? So notice the contrast with this one, where we asked to pass through every edge exactly once, and that's easy. But asking for a cycle in a graph that passes through every vertex exactly once is what's called detecting whether the graph is Hamiltonian, and this is NP-complete. So we don't have and we don't expect to find polynomial time algorithms. Three-colorability. Given a graph, is there a way of coloring the vertices of the graph with 3 colors so that whenever you have an edge, the 2 endpoints are differently colored, also known to be NP-complete. So now we have, I've given you basically some intuition of what the P versus NP problem is. To solve the problem, as I said, of course, coming up with a polynomial time algorithm for any one of these NP-complete problems is one way of solving it. That will prove that P is actually equal to NP. That would be very surprising and unexpected. We think the problem is hard because there is actually no polynomial time algorithm, but that's really very difficult to prove. It's the impossibility results that are hard to establish. So how would we prove the impossibility of a polynomial time algorithm for an NP-complete problem? And one way people took, or one approach which was very popular in the sort of 1980s, and in some sense is still one of the most successful approaches, is to look at circuit models. So the idea is that you take any polynomial time algorithm, it gives for every possible input size a circuit. What do I mean? It's just you look at the algorithm, you fix the size of the input to be some number n, and you kind of unfold the behavior of the algorithm into taking the input. Now the input is n bits. So this is not the variables in my original system. So x1 to xn is a representation. Each one can take a value 0 or 1, but this is a representation of the input instance. And you just unfold the behavior of the algorithm into simple bit operations, which are ands, ors, or nots on these, and you get an output. Now the point is, if you have a polynomial time algorithm, the size of this circuit is bounded by some polynomial in n. Why do this? Well, the point is that writing this way, I mean, algorithms are mathematically very complicated things to define, and to try and prove anything about them is difficult. This kind of allows a certain combinatorial structure, and you can just do kind of, in principle, hope to, apply combinatorial methods to the analysis of these things. But this leads to the definition of what's called P/poly. This is those problems for which, when you fix the value of n, there's a circuit of size polynomial in n which correctly decides the problem. This is not the same thing as polynomial time algorithms. It's more general. Why? Because a polynomial time algorithm gives you not just a polynomial size circuit for every n, but a fixed method for generating them. Here we are not assuming that. Okay, so this is what sometimes called non-uniform P. But the conjecture is that NP is not even included in this. So not only is NP different from P, this is a stronger conjecture, that for a problem which is in NP, well, for a problem which is NP complete, I should say, there isn't even a family of circuits of polynomial size. This is known as, this is a stronger conjecture. What does this really mean? This really means that if you want to solve an NP complete problem, and I allow you the following protocol, I give you the size of the instance, and you can do whatever you want with that. Unlimited amount of computation, do things which are even uncomputable, whatever you like. When you're done with all that, I say, okay, now here's the actual instance. Now you're allowed a polynomial amount of polynomial time computation, right? That's what P/poly really is, okay? And the conjecture says that even that protocol is not enough to solve NP-complete problems, okay? So this is what's called non-uniform P, okay? So that's, now, but the advantage of looking at this is that now we have structure on these, combinatorial structure of circuits is a much simpler thing to analyze in principle than an arbitrary algorithm. And people looked at this to try and prove impossibility results. Now we're nowhere near proving anything like this, but now instead of P/poly, you put further restrictions on the kinds of circuits, and this corresponds to some kind of restriction on the algorithm. So let me give you an example. This was maybe the most successful first approach. Consider graph problems again. Some of them are naturally monotone. What does monotone mean? It means, for example, if I have a graph G and a graph H on the same set of vertices, but which has more edges. So in other words, you get H from G by just adding some more edges to the graph. Now, if G contains a Hamiltonian cycle, then so does H, right? Because a Hamiltonian cycle is a cycle which visits every vertex exactly once. That doesn't disappear when I add more edges, so it's still there. So any graph which contains a Hamiltonian cycle, so does a supergraph. So we say the Hamiltonian cycle problem is monotone. Three-colorability is not monotone. Graph may be three-colorable. I add edges, it stops being three-colorable. But its complement is monotone, right? If a graph is not three-colorable and I add edges, it's still not three-colorable. Okay? So the complement of... Now, because they're monotone, in principle, they can be decided by families of monotone circuits. What are monotone circuits? They're ones which just use AND and OR gates without using NOT gates, right? So back in my circuit, I had three kinds of gates, AND, OR, and NOT. Okay? If your problem is monotone, you don't need NOT gates, right? AND and OR are what are called monotone functions, namely, if you change some of the inputs. Okay, maybe you should, this is a point to explain. How do I put a graph on the inputs, right? My instance is a graph. Well, there are, say this in a bit more detail, there are, let's say, n squared possible edges in the graph. So for each one of them, I will have a binary input 0 or 1. 0 means the edge is not there, 1 means the edge is there. That's how the graph appears. Now, to add edges to the graph means to change some of the zeros to ones. And to say the problem is monotone means when I change some of the zeros to ones, the output cannot change from 1 to 0, right? The output can either stay 0, can stay 1, or change from 0 to 1. Now, and or are monotone functions. Changing their inputs from 0 to 1 cannot make the output go from 1 to 0, but not is a non-monotone function. And or are what are called complete for monotone functions. So any monotone functions can be built up using just ands and ors. So in principle, there are families of monotone circuits for these problems. Okay. But now we can prove that no polynomial size family of monotone circuits will solve some of these problems. Okay, so what have we done? We would really like to prove that no polynomial size family of circuits will do. We don't know how to do this, so we restrict the kinds of circuits for which we can prove that no polynomial size. We know in principle there are monotone circuits, but no polynomial size. So this was down to Rosberg originally, who showed this for the clique problem, not for the two I've had on the previous slide, not Hamiltonicity and three-colorability, but another NP-complete problem. There are no polynomial size circuits. Now, this was in the 1980s, and it's kind of exciting because it's first real, lower bound and impossibility result for some kinds of algorithms at least, right? Monotone algorithms, showing that for some NP-complete problem, there's no polynomial type algorithm of this particular type. Of course, the downside is that there are actually problems for which we know are in polynomial time and are monotone, but for which we can still prove lower bounds. So perfect matching, for instance. We know there's a polynomial time algorithm. As I said, it's not obvious. It's a monotone problem. Adding edges to a graph will not make a perfect matching go away. But we can, Rosberg already showed that there are no polynomial size families of monotone circuits, even for perfect matching. Another kind of lower bound that has been proved on circuits is restricting the depth of the circuit. Okay, so monotonicity was one restriction. We forbid NOT gates. Another kind of restriction is you bound the depth. So the depth of the circuit is basically the length of the longest path from an input to an output. And we have a size bound saying that the size of the circuit grows polynomially in n. Putting a depth bound is a stronger restriction. We say that the depth of the circuit is, say, bounded by a constant. And in that case, we can prove that, for example, no constant depth polynomial size family of circuits decides the parity function. And Rossmann gave a sort of rather surprising result for the K-clique function, showing no constant depth size, well, n to the k over 4 size family of circuits decides K-clique. So this is sort of the story of circuit lower bounds. We would like to prove no polynomial size family of circuits can solve an NP-complete problem, and we are able to prove this by restricting the circuits in various ways, but not for general circuits. So now I want to get to the sort of central notion of this talk, which is to talk about symmetric computation. And I'm going to talk about symmetric computation as yet another newer restriction on circuits for which we are able to prove lower bounds. And I want to show you that this corresponds to a very natural class of algorithms. And so for this natural class of algorithms, we are proving that there is no polynomial time algorithm in this class for certain problems. Okay. So circuits for graph problems. I've already kind of briefly mentioned it. We have families of circuits that decide properties of graphs. For example, so what does this mean? So for each n, we have a circuit where the inputs are n squared, and they're labeled by pairs of numbers 1 through n. So this is going to take as input a graph on n vertices. So the inputs are all the potential edges in this graph, and the input will have a value 0 or 1 to tell you whether that edge is present or not, right? So if the input ij is 1, it means there is an edge between vertex I and vertex j, and if it's a 0, there's no edge. Now, if a graph property is decidable in polynomial time, then we have such a family of circuits where the size of the circuit is bounded by a polynomial. And as I said, the stronger condition, the family is uniform. That is, we can generate the circuit from the size in polynomial time. Okay? If I dropped the second restriction, I would have p/poly over here, the non-uniform version. But now, if the circuit is deciding a graph property, it has a certain invariance condition, which I want you to get. This is kind of the central notion. A circuit is invariant. Now, if I rearrange these inputs by some permutation of n, it shouldn't change the result of the computation. What do I mean by this? The input is a graph, right? Now, the inputs are ij, representing vertex I and vertex j. I and j are numbers. What if I just reorder the vertices of the graph in a different order, but it's the same graph? Okay, that's applying a permutation to the inputs corresponding to a permutation from n. But it's the same graph, so the result of the computation should be the same. Okay, so we say that the circuit is invariant if the output is unchanged under a permutation of the inputs induced by a permutation of n. So in other words, the input is some function, the graph maps the potential edges to 0, 1. We take a permutation of n and apply it to the inputs in the sense that we define pi g to be the function which takes a pair ij to g of pi I pi j. Right? That's what it means to apply the permutation of n to the n squared possible inputs. And we say the circuit is invariant if it accepts g, if and only if it accepts pi g for any permutation pi. This is not the same as saying the result is invariant under all permutations, right? Because there are n squared inputs and we're not taking all permutations of them. To say that it's invariant under all permutations would mean your circuit just counts the number of ones in the input, right? But this invariance condition just says that it's basically the circuit is deciding some isomorphism invariant property of the graphs, right? All the properties of graphs we've talked about, being Eulerian, having a perfect matching, Hamiltonicity, three-colorability, they don't depend on the reordering of the vertices. And so any circuits that decide them are invariant in this sense. Not invariant. Sorry? No. This is the same as, this is really the same as being closed under isomorphism. Okay? Okay, so that's what invariant means. Now, I want to define a slightly different notion, what I'll call a symmetric circuit. A symmetric circuit, in some sense, is invariant, and the invariance is kind of obvious from the circuit in the following sense, that whenever you have a permutation of n and you apply it to its input, you can extend it to a permutation of the whole circuit, which is an automorphism, so it keeps all the connections of the circuits the same. That really means that, so this is it formally, for each permutation, there is in fact an automorphism of the circuit which preserves this. So any symmetric circuit is necessarily invariant, because it's saying not only does the result not change, but in some sense all the intermediate computations are reproduced for all the permutations. That's what we call sort of an explicit, it's kind of sometimes called explicitly invariant circuit. The invariance is inherent in the structure of the circuit. But there are invariant circuits which are not symmetric. So this is like the case with monotone. I described a class of problems as being monotone and said that in principle you can get rid of the NOT gates. But not everything which is syntactically monotone, in the sense doesn't have NOT gates, not every circuit which is semantically monotone, meaning the result is monotone, is syntactically monotone. So similarly, not every invariant circuit is symmetric. And in fact, one of the things we showed was that, so in principle, when you have a graph property, isomorphism invariant graph property, it's decided by an invariant circuit. It can also be turned into a symmetric circuit, but converting it again possibly requires a blow up in the size, just like with the monotone that's kind of one of our results. Now, why are we interested in symmetric circuits? Well, we came to this from considering logic. So FPC is class of decision problems definable in fixed point logic with counting. I'm not going to define fixed point logic. In fact, this is the only mention of the logic there will be in the slide. The point is that this is, in some sense, a high-level language. High-level meaning not in terms of the operations on individual bits, for describing graph properties which are in polynomial time. So decision problems are isomorphism in closed classes of finite structures, like graphs, Boolean formulas, systems of equations. And we are able to show that a graph property is definable in this language if and only if it's decided by a uniform family of symmetric circuits. So here, this is symmetric in the sense I just defined, using and, or, not, and majority gates. So we need one additional kind of gate. A majority gate takes some number of inputs and gives you an output 1 if a majority of the inputs is 1, 0 or otherwise. So you need one additional kind of gate. Now, you can convert this into still a polynomial-sized circuit without majority gates. That's a general rule, but you'll break symmetry if you do that. So you need this. Excluding majority gives us something strictly weaker if you still require the circuits to be symmetric. Okay, so this is, for our purposes, we can take this as the definition of FPC. In fact, we can prove something now, so this is kind of a robustness property. Say you have a Boolean function, so it takes some string of zeros and ones and gives you 0, 1 output. We say the function is symmetric. This is a different use of the word, mind, if it's invariant under all permutations. This is what I mentioned before. This means the function just counts the number of ones and gives you some property of the count. Note that all of these, and, or, not, and majority, are symmetric functions in this sense. And we can say that, in fact, you allow any additional kinds of gates, as long as they're symmetric and the circuits are symmetric in the other sense, then you're still in the same class FPC. So this is a fairly robust definition. And it defines a natural notion of what I call polynomial time symmetric computation. Right? So computation which is inherently respects the symmetries of the input, okay, and doesn't impose some kind of order, treating inputs differently based on their position in the input rather than on the inherent properties of on the inherent symmetries of the input itself. So this is a robust and natural notion of things which can be done by algorithms which are sufficiently symmetric, which means sufficiently abstract. They respect the abstraction inherent in the input. And now we can actually, turns out, we can prove lower bounds for this. I already told you that translating these into, say, getting rid of the majority gates would require breaking symmetry. And we can prove something more. We can show, for some NP-complete problems, they're provably not in FPC. So provably, they do not admit polynomial time symmetric algorithms. Okay? Among them, satisfiability of Boolean formulas, the classic NP-complete problem. And I should have, because that was my first example, I should have said also solving systems of linear equations over the natural numbers. Hamiltonian cycle, three-colorability, for all of these, we have proofs that they are simply not in FPC, categorical proofs, right? On the other hand, there are other NP-complete problems for which inclusion in FPC is still an open problem, and in fact, equivalent to P versus NP. Okay, I can formulate some problems for which, if you could prove they're not in FPC, you would separate P from NP. I don't have a nice, snappy, simple one, but I can give you some examples later. Upper bounds. Turns out that things which are kind of obviously polynomial time turn out to be in FPC. What do I mean by obviously polynomial time? Well, just, actually, this is not, I mean, the most common kinds of operations, deciding whether a graph is Eulerian is in FPC, right? Just because that's counting the degree of every vertex, that kind of thing. And many, what I would call non-trivial polynomial time algorithms can be expressed in FPC. There's a monumental result by Martin Grohe, which says that any polynomial time property over any proper minor closed class of graphs is in FPC. So this is kind of what I would call highly non-trivial polynomial time algorithms, the whole kind of machinery of Robertson and Seymour graph structure theory reproduced inside FPC. Eulerian cycle, I mentioned before, perfect matching, the existence of a perfect matching. This is, again, not obvious. Even the polynomial time algorithm requires a bit of work, but it's whether it is included in FPC was an open question formulated in the late 90s by Gurevich and Shelah and not solved until about 15 years later and required some interesting new methods, which maybe I'll tell you a little bit about. Solving systems of equations over the rationals or the integers, right, which I told you right at the beginning are polynomial time, you can in fact show they're also in FPC. But there are in fact still polynomial time properties which are provably not in FPC. This was already known 25 years ago in some sense by Seyfer-Immermann, but maybe a more natural problem, XOR-SAT, or simply solving systems of linear equations over a finite field. Another example I had right at the beginning of a property in polynomial time, it turns out cannot be done in FPC. And this means, interestingly, that the Gaussian elimination algorithm, which I started with as an example of a polynomial time algorithm, is not a symmetric algorithm and cannot be made symmetric without a big blow up in size. Why is this? Well, the Gaussian elimination algorithm, crucially, at each stage, you choose a pivot, right, around which to do the calculation. So in other words, you're looking at a system of equations. What do I mean by the symmetry in this case, right? It means that if you permute the variables, which permute the columns of the matrix or permute the rows, the algorithms should still behave in exactly the same way. But the Gaussian elimination doesn't. It depends upon treating the rows in a particular order and choosing the pivot. You can symmetrize it by kind of doing in parallel all the different possible pivots, but that involves an exponential blow up in the size of your circuit if you do it as a circuit. And what this result proves is that's unavoidable. You cannot do Gaussian elimination and keep your algorithm symmetric. Okay, so then how is it that solving systems of linear equations over the rationals can be done by a symmetric algorithm? Well, you don't use Gaussian elimination. The rationals have rather more structure than a finite field. Crucially, they're ordered, right? And that means we go for a rather more general result. Rather than just solving systems of linear equations, you can solve equations and inequalities. This is linear programming. And now linear programming is a very important algorithmic tool. Large variety of optimization problems are solved using linear programming. We know it's in polynomial time since 1980, the work of Kacyan. So what is linear programming? We have a collection of constraints and a set of variables. Each constraint, let's say, is a rational vector and a rational constant. And we want to find, given this collection of constraints, whether there is a solution, namely there's an x, which satisfies this inequality for all the constraints. Okay, that's what linear programming problem is. Instead of equations, I have inequalities. And there's a corresponding optimization problem where you have a collection of constraints and you also have a linear function you're trying to optimize, minimize or maximize, as the case may be. And we showed that these things are expressible in FPC. And basically, the ellipsoid method of Kacyan can be translated into FPC. So let me give you some idea of what's involved here to see what's different from the Gaussian elimination case. So what is the ellipsoid method, very roughly speaking? We have a collection of constraints. They determine in n space, right? So n is the number of variables, so the number of dimensions, a polytope. So I've drawn it in 2 dimensions because that's what fits on a slide. Okay. So this is a system of 1, 2, 3, 4, 5 linear constraints. And together they define a region. In this case, it's a non-empty region, so the solution is feasible, right? But what we're given is a system of constraints, and we want to know, is there a solution? How does the ellipsoid method work? It says you start with some point. You may as well start with 0. And you check, does it satisfy all the constraints? The answer here is no, because it's outside that region. But now it says, based on the bit complexity of these different constraints, you can calculate a certain ellipsoid around this point, which is guaranteed to include that. Okay? Now we know that if there are any feasible points, they're inside this ellipsoid, and we know that the center of the ellipsoid is not in the region. So what we do is we choose one linear constraint that is violated by this point, project it onto that, and then we can calculate a new ellipsoid centered around that, which is still guaranteed to constrain this, but is at most half the volume. Okay? The fact that it's at most half the volume means if you iterate this procedure, you either end up with a region so small that you know that the original one must be empty, or you find a point inside the region. I mean, those are the two possibilities. And this happens within a polynomial number of steps. That's the ellipsoid method. Now, why can we do this symmetrically? All the calculations involved, because they're kind of over an ordered domain of rationals, we can do in FPC, right? Even though we have to make sure that we're manipulating matrices where in a symmetric fashion, which means all our calculations have to be invariant under permutations of the rows and columns. That's all fine. What's not so obvious is how to choose the violated constraint, right? So here at this stage, I said we choose a constraint and project. Choosing is a symmetry breaking operation. Why do I choose this one rather than any of the others? And each choice would lead to a different computation. And if I do them all in parallel, I will get an exponential blow-up, like with the Gaussian elimination. But the point is, I don't need to choose, because the ellipsoid method, and this Kashian already proved, works as long as at each point I have some separating hyperplane. In other words, it doesn't have to be one of the constraints. It could be anything which touches the polytope and separates my current center from the polytope. So in particular, I can just take all the constraints that are violated and sum them. By the linearity of the system, this thing is, in fact, a separating hyperplane, and that's all I need. Okay, so this symmetrizes the ellipsoid method and shows that we can do it. And this proves, for instance, that what my claim at the beginning, that solving systems of equations of the rationals is in FPC. We can do it by a symmetric algorithm. But this doing linear programming led to a very interesting question, right? Because for many NP-complete problems, linear programming is used in practice for giving approximations, right? We have a problem for which we don't know how to solve exactly in polynomial time, so we settle for approximate solutions. And some of the best approximations come by coding the thing as a linear program. So for example, consider the vertex cover problem. Here I'm given a graph, and the problem is to find the smallest set of vertices such that every edge has at least one point in this set. Right? This is what we call a vertex cover. So never mind find the smallest set, let's say find the size of the smallest set. One way to translate this, one way to do this is to translate it into the following linear program. My problem, I have an objective function, okay, what is this? I take the graph, for every vertex in the graph I have a variable xv, and I say, minimize the sum of these variables subject to the constraints that each variable takes a value between 0 and 1, and for every edge in the graph, the sum of the two endpoints is at least 1. So note that a solution to this, which only used values 0 and 1, would in fact be a vertex cover, right? Because every edge, in other words, you take the set of variables which are set to 1, then every edge has at least one endpoint in the set by this constraint, and the minimization condition tells me I get a smallest such set. Okay? So a 0-1 solution gives me a vertex cover. But this linear constraint just says these things can be now fractional. I can give some fractional weight to every vertex, right? And this is what's called a fractional vertex cover. And it's some approximation of the value of the vertex cover. It'll give me something in general smaller than the vertex cover, because I've allowed myself fractional solutions. But solving a linear program I can do in polynomial time. So this gives me an approximation. In fact, it can be proved that the linear programming relaxation achieves an approximation ratio of 2 and no better. What does that mean? Whatever value you get over here is at least half the size of the smallest vertex cover. But there are graphs in which it is no more than half. So we know it does no better than approximation factor 2. Now, people have considered various ways of strengthening this linear program by adding what are called extension variables. So you have not just variables for vertices, but you add additional dimensions to effectively build more complex polytopes whose projection down still gives you a vertex cover. Consider semi-definite programs rather than linear programs, et cetera, et cetera. Now, if we show that these various, we're able to show that many of these standard extensions are still symmetric, still solved by the ellipsoid method symmetrically and therefore in FPC. And we can prove a lower bound in FPC. We've been able to prove that any symmetric algorithm, anything in FPC, cannot achieve approximation better than square root of 2. We think this can probably be improved to 2, but we don't know how to do this at the moment. I mean, we conjecture this can be improved to 2. But certainly, so in particular, no symmetric algorithm can solve it exactly. No symmetric algorithm can give you an approximation better than about 1.4. But actually, I realized maybe square root of 2 is a bit optimistic. I think the one that we have, I should claim 1.36, we can certainly prove, okay? But I think we can do the square root of 2 also. But so this is a sort of real lower bound showing for a class of algorithms, symmetric algorithms, we cannot do better than this. There is no polynomial time algorithm that will solve it exactly. But now I claim that this is for an actually interesting class of algorithms because it includes the algorithms which are most commonly used for approximating things like vertex cover, like the semi-definite programming, relaxations, etc. Okay? So no symmetric polynomial time algorithm can achieve a ratio better than this. Okay, so this kind of leads me on to my concluding remarks. So what I wanted to convey to you is, first of all, we have this thing called FPC, which defines what I call the natural notion of symmetric and polynomial time computation. It is a proper subclass of P because there are problems in P which we can prove are not in FPC, like solving systems of linear equations over finite fields. Okay? But still, it's a remarkably powerful subclass and able to express many non-trivial polynomial time algorithms. And for that, I cited Groe's result, for example, that any minor closed, proper minor closed class of graphs is, for example, decidable in FPC. And things like the ellipsoid method for solving semi-definite programs and so on turn out to be in FPC. So it includes some of the strongest algorithmic techniques for approximating NP-hard optimization problems turn out to be in FPC. And since we are able to show for some of them that no algorithm expressible in FPC can solve them exactly, right? This establishes limitations on the most commonly used approximation technique. That's what I meant by limits of symmetric computation. And the final thing I wanted to say, this is a sort of a glimpse, because I think there is in principle a rich theory of symmetry in computation. There are many other strands. I mean, I talked about essentially complexity theory and symmetric algorithms, but symmetry arises in various other things. I mean, I could have talked about work on the graph isomorphism problem or constraint satisfaction problems or even various things in databases where symmetry turns out to be an important consideration. And the same kinds of methods kind of pop up. And the methods, which I have not said that much about, build heavily on the mathematical tools of symmetry, namely the study of finite permutation groups. I didn't tell you much about the methods here, but of how we prove sort of the lower bounds for FPC are proved by methods and logic, but the equivalence with symmetric circuits relies heavily on work on analyzing the action of permutation groups on circuits and so on. So I want to leave you with the message that symmetry in computation is an exciting and emerging field within theoretical computer science, which combines study of abstraction, right? Looking at input structures abstractly and their symmetries, with the study of complexity, which is usually done in terms of what I would call low-level, bit-level complexity. And this kind of seeks to combine those two. And I'll end there.
Thank you very much for your very